Welcome to the third experiment of EEE 306 Control System Laboratory. So for this experiment, we will design compensators to improve the performance of a second order system. We will improve the performance of both transient and steady state portions of the response. And for this, we will use both lag and lead compensators whenever necessary. So you have already done an experiment on PI, PD and PID controllers. So we will basically do similar things here. A bit different will be the format, but the outcome will be somewhat similar. We will try to improve the performance of a second order system in both steady state and transient. So there will be some parameters of our interest. We will analyze or use these parameters to actually assess the performance of the system. One thing to note here, experiment 3 and experiment 4 are very closely related experiments. For experiment 3, we will design a lag compensator and a lead compensator. Separately, we will separately use a lag and a lead compensator to improve the performance. We use lag compensator to improve the performance, improve the steady state performance, and we use the lead compensator to improve transient performance. In the next experiment, or experiment 4, we will use the combination of both lag and lead to actually improve both these performances. So, if you understand experiment 3 pretty well, then experiment 4 shouldn't be a problem. So I will upload these two experiments in very quick succession. So that's the first thing that I want to mention here. The next thing that I want to mention here is experiment 3 basically requires the idea or the knowledge of root locus. I assume that you have already known how to draw the root locus. You already have the knowledge about drawing root locus from your theory course. So I will not go into the detail about how the root locus is drawn. For better understanding, for the sake of your better clarity, I will upload some random YouTube videos on drawing root locus in Bugs. You can just get back to it and get some idea about how to draw root locus. For the experiment, I will just use the MATLAB command for drawing the root locus. And that's all. So I was talking about some parameters of interest, and they are these 4 parameters. Settling time TS, peak time TP, overshoot percentage, percent overshoot, and steady state. So I will basically have these 4 parameters of interest, and these 3 will indicate transient performance, or we will use these 3 parameters to actually assess the transient performance, and we will use this parameter to assess the steady state performance. Okay, so let's get some more detail about these things. As we are doing the experimental aspects of these parameters, I am not going to the definitions of the details, how we can define them and all. I am just going to use the formulas of these parameters. If you want the theoretical understanding or the basics behind them, you can just go back to your theory lectures or the book. It's explained pretty well in the 4th chapter of NIS. If you want explanation, you can go there, but I'm just listing out the formulas which will be required for this experiment. Okay, so we already know that dominant pole of a second order system is formulated by this. There are 2 poles, so 1 and 2. These 2 poles are complex conjugates of each other, minus zeta omega n plus minus j root over j omega n root over 1 minus zeta square. So zeta is damping ratio, and omega n is natural frequency and damping ratio. So the settling time Ts is 4 by zeta omega n, peak time Tp is pi by root over of 1 minus zeta square, and the percent overshoot is e to the power minus pi zeta root over 1 minus zeta square. So you have to memorize these formulas. So for memorizing this in a very efficient way, I can suggest you something. It's just my suggestion. You can obviously memorize these formulas straight away, but for better memorization, I am just giving you some tips. You can see this is the dominant pole, right? So it has a real part and an imaginary part. So the real part has the numerical value of zeta omega n, and imaginary part have a numerical value of omega n root over 1 minus zeta square. I'm just taking the numerical values of the modulus. So you can say that Ts is 4 by real. You can see zeta omega n is real, so 4 by real. You can say that Tp is equal to pi by imag. You can see the imag is here, omega n root over 1 minus zeta square. I'm sorry, is omega n here. So these are basically same. So Tp is pi by imag, and percent overshoot is actually e to the power minus pi multiplied by real by imag. So real is zeta omega n. So if you just put zeta omega n here, and imag is omega n root over 1 minus zeta square. So omega and omega cancels out, and it's basically e to the power minus pi zeta divided by 1 minus zeta square. Exactly the same thing. So you can use these trick formulas to memorize this, or you can just use the conventional ones, whatever you think is good for you. So let's now go back to the experiment. We have had some background information. Now let's go to MATLAB. Okay, so let's check the lab sheet. So we will use, oh, one thing I have forgot to mention. Both lag and lead compensators have the same transfer function. G lag and G lead, they both have the same transfer function. And they're often associated with a gain. So you can see they're basically the same transfer functions, both lag and lead. For the case of PI and PD, they were basically different functions, but for lag and lead compensators, the function is basically the same. S plus ZC divided by S plus PC. S plus ZC divided by S plus PC. So what's the significance of this transfer function? If you multiply this with a system, then obviously this compensator will add a 0 and a pole to the root locus, right? Because there will be a 0 at minus ZC and a pole at minus PC, depending on the values of ZC and PC. So we will get a 0 here and get a pole here. The difference between lag and lead compensators is the value of ZC and PC. You will see that for a lag compensator, a PC will be much less than ZC, and for the lead compensator it will be opposite. PC will be greater than ZC. We will just explore these things in the experimentation phase. Okay, so the first task is designing a lag compensator, and lag compensator is designed to improve the steady state performance. So it's mentioned here that you have a transfer function like this. So GS is equal to 1 by S into S plus 2 into S plus 10. Okay. Our task is that we have to design a lag compensator for the system operating with overshoot of 20% to reduce the steady state error to a ramp input tenfold. So if I break that down, this means we have this function. It is stated that our overshoot is 20%. We have to reduce the steady state error of this system by tenfold. That means if my error is now E, after using this lag compensator, my error should be E by 10. And the input here is ramp input. Okay, so now we know our basics. The first thing that we need is we have to calculate our zeta from this overshoot. We already know the formula. Let me just carry this out for you. So we know that the percent overshoot is 20. So OS is basically percent is basically 20. So OS is basically 0.2. So the formula of OS is e to the power minus pi zeta root over 1 minus zeta square. So you can just do some calculations, use some ln here over here, and it's just a basic algebra. You will reach this stage, that zeta is equal to root over of 1 by 1 plus pi by ln s whole square. I always use this formula to get back here. If you want, you can memorize this as well. So if you put your OS to be 0.2, then the zeta will come out to be 0.4559. So from now on, as the overshoot is fixed, the zeta will also be fixed. We cannot change zeta whenever we are designing this lag compensator. So after that, as I have already said, the transfer function of lag compensator is something like this. It has a gain k, and it has 0 at z lag and pole at p lag. Depending on the value, it will be minus. So minus z lag and minus p lag. So for ramp input, we already know. Let me just. So for ramp input, we know that the steady state error equation is this one. I'm just listing out all the three steady state error equations. So for step input, it is 1 by 1 plus kp for step. For ramp input, it is 1 by kv, and for parabolic input, it is 1 by ka. So what is kp? kp is limit s tends to 0 gs. What is kv? kv is limit s tends to 0 s gs. What is ka? ka is limit s tends to 0 s square gs. Now again, I am not going into the details of how these equations are derived. These are all provided in the book and also should be discussed in your theory class as well. So you should get these things from your theory or the book, whatever you want. I just need you to remember these formulas. You have already done some experiments on these formulas as well. So for this experiment in particular, we need the ramp function, ramp input. So we don't need any other thing. We just need the ramp. So let's erase all this. So for the ramp function, we have e to the power infinity is equal to, as I said, 1 by kv. kv means limit s tends to 0 s gs. So now our previous error was without the compensator. My error should be 1 by limit s tends to 0 sgs. I'm just putting the value of gs over here. The gs was, I guess it was s plus 2 s plus 10. So ss is gone. So if I just put zeros over here, E5 will be simply 20. Infinity, I'm sorry, will be 20. So this is our uncompensated error. So when we are going to compensate this error will become E dash infinity, it will be 2. Why 2? Because we are asked to improve the steady state error by 10-fold. That means if the error is 20 previously, now the error should be 2. So now our error should be 2. Now we can just back calculate this to get our z lag and p lag. Let's do that. Now we know that the compensator system is z prime s, which is s plus z lag by s plus p lag into the previous thing, s plus 2 s plus 10. Oh, as same as the previous. Let me just write over here. G dash s is equal to the multiplication of the compensator and the original system. So in the compensator we have s plus z lag by s plus p lag. For the system we previously had 1 in the numerator, so I'm just taking it empty. Multiplied by s plus 2 s plus 10. So for this thing we now have an error of 2. So e dash infinity is equal to 1 by limit s tends to 0 s multiplied by this one. There is a s here, so this s and this s will be cancelled out. So I'm just writing this like this. S plus ZL by S plus PL, S plus 2, S plus 10. So if I just put the limit, it will become S plus PL. I'm sorry, S will be gone because S is 0. PL 2 10 by Z. So this is again 2 as we have already determined. So 2 is cancelled out, and finally we get that Z lag by P lag is equal to 10. So we get this Z lag by P lag is equal to 10. So this is our final result. You can see that here as well. It is done a bit differently here. You can use this fashion as well. I'm just doing it from scratch. If you want, you can just go by this. So now we know that our location of 0 will be at a distance which is 10 times compared to the location of pole. So if our pole location, we assume that the pole location is 0.01, we will assume this pole to be as close as origin. You can use 0.01 or you can use 0.001 as well. It's your choice. I'm just using 0.01. So the Z lag will be 10 times this. So it will be simply 0.1. So now we know the Z lag and P lag. Let's go to the modeling portion. So let's go to the MATLAB. Okay, so I've already written the code here. So let's see. The regular drills, clear all, CLC, clear all and close all. Then we are defining this S as transfer function. So then this is our uncompensated system. S equal to 1 by S into S plus 2 into S plus 10. You may find a different transfer function when you will go for an exam. So just mind this. So now R locus is the command for drawing the root locus. Okay, and S grid, this S grid will help you to find out the intersection between this S grid line and the root locus. So the intersection between the S grid line and the root locus will actually be our dominant pole, and this S grid line will be drawn as a function of this zeta that we calculated. So depending on the zeta, we will have a line on the root locus, and we will try to identify the intersection of that particular line and the root locus. So we will just find that out. We will actually find out the point of intersection using this rlocfind command. This rlocfind command is actually used to specify a particular point in the root locus. So if you have the root locus and you are using this rlocfind command, then this whatever point you choose, this command will give you back the k or the gain and the dominant poles corresponding to that point. Whatever point you choose on root locus, this command will give you back the gain at that point and the poles at that point for the root locus. So we will need these two. So after that, we will design the closed loop system by giving the feedback. Now the gain is added, and then we will just check the step response. This is for uncompensated system. Whatever we are doing, these are for uncompensated system. We are not using any compensator yet. So that's done. In the next portion, we will use our compensator. So we already know the values of Z lag and P lag. You can see that the P lag is 0.01 and the Z lag is 0.1. So now we have the compensator system, and that is, as I have said, the multiplication of the original transfer function and the transfer function of the compensator, which is named as lag. So again, we will just draw the root locus, and as the overshoot or the zeta is fixed, we will again use that S grid command to draw that line. On this particular line, every point has the same zeta or overshoot. So this S grid we'll take the zeta as input, and zeta is obviously 0.4559 as we calculated. Again, we will use this unlock find command to actually specify the point of intersection between the new root locus and that particular line corresponding to our zeta value. So again, we will get the gain and pole corresponding to that. Now as we have the gain, we will now use the gain and use the unity feedback to get our closed loop. And on that closed loop transfer function, we will now again draw the step response and get the step info. Finally, we will just compare the outputs. You already know the functionality of lsim command. I'm not going into the detail. We will just observe these graphs when we draw. Let's just run one by one. Let's just run this section. So as I have said, this is the root locus of the uncompensated system. I will not explain how this root locus is derived. I encourage you to find out this root locus by hand, but we are using the root locus command here for drawing this root locus. This is the command rlocus. Rlocus command actually plots the root locus of a particular transfer function G. Then this rlock find function has given you this cursor that is moving. Our job is to place this cursor on the point of our interest. Now, what's the point of our interest? Our point of interest is the intersection of this root locus and this line, this dashed line. You can see it's noted 0.456 or 0.4559 as a matter of fact. This is that particular line we have drawn using the sgrid command. Sgrid command draws this particular line based on our zeta value, which is 0.4559, and on this line, whatever point you will choose, the overshoot or the zeta will be always fixed. So our task is to specify this particular point of intersection. I want you to be as precise as possible. I'm just trying to be very precise. It doesn't matter if you miss the exact point by some margin, but don't be very off. Don't just press the mouse here. You have to be as close as possible. So let me just, you can choose any of these 2 points. There are 2 points of intersection. You can just choose any of these 2 points. There are 2 points because we will get 2 dominant poles which are complex conjugates. So it doesn't matter which point do you choose. So let's choose the upper one. I am trying to be very specific. Okay, I think this is very close. Okay, I think this is very close. So let's just right click it. So we also got our step response. So this step response is the step response corresponded with uncompensated system. Okay, so this step response is already very good, because you can see at when the time has approached to 30 seconds after some time from initial transient phase, you can see we have got our desired response because it is 1. For some cases this will not be 1, this will be very less than compared to 1. Let's say it will be 0.8 in some cases. So we will mainly use this lag compensator in those cases where the steady state response is not 1, because we expect it to be 1. Step function means that when the time is greater than 0, the output should be 1. So we expect it to be 1, and in this case it is very close to 1. So for these cases we will not use actually lag compensator. It's just a demonstration process, so anyways we are using this function. But in practical cases you will need to use lag compensator for those functions whose step response will not give you perfect 1. Let's say after some time the steady state value is 0.8. So there is a big gap between our desired result and our achieved result. In those cases, we will mainly use lag compensator. So let's get back to the code. The values are saved from this section. Now we will run the next section. So in this section, we will actually we have actually designed the lag compensator and multiplied it with the original system, and then again we have plotted the root locus using rlocus command, and then the sgrid command and rlocfind command to actually specify the intersection point, and then again finally we will also get the step responses. So let's just run this section. So again there is a root locus and a cursor due to rlocfind. So this time the root locus is a bit different because some modifications are done, but there is a still a dashed line due to the sgrid command, and basically on this line, as I have said, every point has the same zeta value. So our task is again to be very specific and choose the intersection point. I'm choosing this intersection point very carefully. Okay, so this one. So as you can see, using the lag compensator hasn't actually done much, because as I said, the step response was already very perfect in terms of steady state errors, so it hasn't done much. So let's see. So this is our step info. So this was our step info without the compensator. You can see the overshoot was 26%, which is actually very close to 20%. It will not be exactly the same. And for the compensator system, the overshoot is 30%, which is again very close to 20, because we are using the formula of second order system, but the order is 3 here, so it will not be exactly same, but it will be very close. So yeah, so our task was to improve the steady state error, and let's see how the steady state error has worked out. So this is our final stage. We will get to see the errors here. So let's run this section. So here you can see, I am not explaining this graphs because you are very familiar with the LCM command already. So this blue line is the input line and this red line is the response line. You can see this is for uncompensated system and this is for the compensator system. You can see that for the compensator system, the red line is even more closer to the blue line on the input, and that this black line is the error. You can see the error here is actually, we can figure this error out. It's a very small error, but as I have said, the step response was already very accurate, so there will be a very small error. So there is a very small error, but when we are using the compensation, the error is decreased even more, and the error is actually decreased by 10 times, as we have chosen the Z lag and P lag in such a fashion that the ratio was 10. So the error you can see here is very small compared to the previous error. So this was our objective, to decrease the steady state error. So one thing to note here, that in this case the function we are using already had a very good response in terms of steady state performance. So the results that we have achieved wasn't that visible because the error was already pretty less, but in some cases the error is very high. So in those cases you will actually get better results when you use a lag compensator. So the main purpose of lag compensator is actually improving the steady state response. So that's all for lag compensator. I will come back with another video on lead compensator.